So hi everyone, today we'll start discussing about one of the most popular subjects in computer architecture, which is named pipelining. This technique enabled the second revolution in CPU development history and led to have very fast CPUs with instruction level parallelism. The term pipeline is an analogy in that there is a fluid in each link of a pipeline as each part of the processor is occupied with work. So the machine with different parts will have different works to do, and a single work will be completed by going through different stages, and none of these stages stay idle while processing multiple works together. Main objective with pipelining is to reduce the cycles per instruction performance metric, CPI. In other words, suppose that we have a three-stage pipeline for each incoming job, so that each job is divided into three sections corresponding each pipeline stage as shown in this figure. So the processing each instruction takes 3 clock cycles to finish. Without pipelining, every instruction must wait until the execution of the other is over. In that case, if we have n instructions, then we are going to have to wait for 3n cycles. However, if we pipeline the stages of these instructions as shown in the figure, we will have 3 plus n minus 1, in other words, n plus 2 cycles to finish the whole work. So for each of these cases, CPIs will be 3 for the unpipelined and approximately 1 for the pipeline cases. So given that we can pipeline all n instructions as shown without any problem, we can reduce the CPI to 1 for large n, which is the optimal value for single cycle computers, if you remember. But it's a multi-cycle where the CPI is now converging to 1, which is really optimal, which is really good. So let us think about the number of stages in a given RISC architecture instruction set and the pipelining relationship with the RISC instruction set architecture. So there are in fact 5 basic pipeline stages for this instruction set. The first stage is the instruction fetch cycle, in which the 4 bytes of memory is read and it points to the instruction that needs to be executed. If you remember from MIPS, MIPS is a great example for RISC architecture. Second stage is the instruction decode and register fetch cycle. We decode the instruction and at the same time read in the values of the registers involved. As the registers are being read, do the quality test in case the instruction decodes as a branch or jump. Instruction can be decoded in parallel with reading the registers because registers' addresses are at fixed locations. Next is the execute cycle. If a branch or jump did not occur in the previous cycle, the arithmetic logic unit, ALU, can execute the instruction. As for the memory address, there are 2 possibilities, load and store. Loads reads memory and loads it to a register, whereas store writes a register content to a memory address. Final stage is the write back. And in that case, something gets written, final result, for example, might be written back to the one of the registers in the register file. Simple operation, whether the operation is a register operation or a memory load operation, the resulting data is written to the appropriate register in that particular particular stage. As can be seen, different instructions take different amounts of clock cycles. For example, branch instruction takes two clock cycles. Store instruction takes 4 clock cycles, whereas the rest of the instructions, most of them actually, take 5 clock cycles. So the idea behind pipelining is to overlap operations and gain some instruction level parallelism. So the main question is that, can all 5 stages for each instruction overlap? The answer is almost, but not all of them. We'll see examples of that. In other words, there are many problems with trying to implement this. Obviously, we can have ALU performing an add operation and a multiply operation. I mean, having ALU doing all these 2 operations at the same time is impossible. The memory is accessed twice during each clock cycle. This problem is avoided by using separate data instruction caches. So Princeton architecture will probably cause more problems than a hardware architecture as far as the pipelining is concerned. We write in the first half because therefore a write operation can be read by another instruction further down the pipeline. The use of pipeline registers allow the CPU to have a memory to implement the pipeline. We use an adder to implement PC, the program counter, by the end of the instruction fetch. Within the instruction decode, we may branch and modify the program counter. How does this affect the pipeline? So we need to be pretty careful about the program counter updates and its connection to the pipeline implementation. The performance gain from using pipeline occurs because we can start execution of a new instruction each clock cycle. In a real implementation, this is not always possible. Another important note is that in the pipeline process, a particular instruction still takes at least as long as to execute as non-pipelined. pipeline hazards prevent the execution of the next instruction during the appropriate clock cycle. Hazards consist of the set of exceptional cases for the previous overlapping not to function properly. There are three types of hazards: structural, data, and control. Structural hazards occur due to limited resources of the data path hardware. Data hazards occur when there is an instruction in the pipeline that affects the result of another instruction in the pipeline. So the output of one of the instructions could be an input to the next instruction. Finally, control hazards occur due to the pipelining of branches and other instructions that change the program counter. If a hazard occurs, a delay line is introduced and the pipeline stalls temporarily. So let us consider the performance. Before going into details of the hazards, let's consider the performance of a pipeline multi-cycle computer. The pipeline depth is defined to be clock cycle time on pipeline divided by the clock cycle time pipeline. So if you use 5-stage pipeline, the depth will be 5 in this case. This formula can also be used to compare two pipeline computers with different frequency of operation. The speed up can be found by adding the effect of pipeline stalls into the equation as shown in the denominator. We finally multiply it by the pipeline depth to find the speed up. Assume that you need to compare two processors, one with a structural hazard that occurs 40% of time, causing a stall. Assume that the processor with the hazard has a clock rate 1.05 times faster than the processor without the hazard. So both processors are pipelined and the number of pipeline stages are the same, let's say. And how fast is the processor with the hazard compared to the one without the hazard? Well, it is given by at the bottom of the slide, and if you just crunch in the computation details, this case, the calculation yields 75% slower processor. So the hazards affecting the pipeline also affects the speed at which the CPU can operate in practice. So structural hazards happen with different instructions fight for the same resource, as we said before. For example, to that is the following. Suppose a processor can only read and write from the registers in one clock cycle. This would cause a problem during the instruction decode and write back stages, because in both of these stages we make register file accesses. And second example, assume that there are not separate instruction data caches like we have seen in Princeton architecture, and only one memory access can occur during one clock cycle. In that case, a hazard would be caused during the instruction fetch and memory cycles. A natural solution to the structural hazard is to stall the pipeline or put a pipeline bubble into it to make it pause temporarily or stall temporarily. Second type of hazard is known as the data hazards. We provide an example, an example set of instructions to help show a possible data hazard that it can occur in a pipeline. As you can see, the main problem here is that instructions are trying to access data that's not available at the time of request. For example, subtract instruction, is trying to access the contents of register R1, which is the output, actually, the output of the previous instruction that needs to be written to the register 1, but which is not yet done. And these cases, are shown in with bold red lines. Here we cannot expect the program to reorder his or her operations, thinking that there's a pipeline underneath. You can assume, for example, this to be the only code we want to execute. So we need solutions to resolve this problem. There are ways, for example, in the software level by introducing no op or no operation instruction whenever two instructions in sequence would cause a data stall or data hazard. Alternatively, we can implement such no-ops or bubbles in the hardware. As you might guess, introducing no-op operations will cause us to lose some cycles, increasing the CPI. So there's a better way, which is the best of all, and is known as data forwarding. Before we talk about data forwarding, let's consider the problem with detection of data hazards. Because before we solve some problem, we need to know that there's a problem, right? To detect, we add 6 extra registers as named in this figure so we can forward register numbers through the pipeline. These registers are in addition to other pipeline registers. If you think about it, you will realize there are 2 outputs that might be valuable for the rest of the instructions. These are the ALU output and DM output, data memory output. If you load something into the registers. So if the inputs of the ALU block request one of these outputs, we detect the data hazard. Of course, this is true under the assumption that we write control signals for EX and MEM WB registers, write back registers, being on one because otherwise these registers are not written, and hence no instruction that can cause a hazard is processed by the processor. The detection logic introduces more combinational logic as well as registers into the microarchitecture. Okay? After detecting the data hazard, next thing is to implement the data forwarding. Data forwarding is based on the following question. When a data hazard is detected, is the result available somewhere else in the pipeline? The answer is almost yes. In other words, data forwarding can be used to solve data hazard problem to some extent. To implement data forwarding, we need to bypass the pipeline register flow. An example is shown to solve the data hazard problem in this slide. As you can see, the ones with red lines are real hazards. The rest is going to be just okay because at those times the data will be accurate to read and write. To be able to implement this in the microarchitecture, we would need a MUX, a multiplexer before the ALU, and the inputs from EXMEM and MEM write-back pipeline registers can be inserted into ALU, which will be controlled by the control logic. So this will, of course, increase the number of control bits. Here's another example. At the output of the ALU, we already have value that's supposed to be stored in R1. So we connect that to the input of the ALU for the next instruction. Similarly, we have two other connections as shown in the figure. You can walk through this example to convince yourself indeed such a data forwarding logic will help with the data hazard. So we don't need to really put extra stalls or pipeline bubbles into our pipeline stages in order to prevent data losses or data hazards. Though we need extra special hardware to decide on the data forwarding. An interesting question could be, can data forwarding prevent all data hazards? And the answer is unfortunately no. For this example, data forwarding, for example, is unable to fully resolve the data hazard present in the pipeline. Using our well-known methods such as stalling pipeline can help resolve it. So the stalling or putting a pipeline is inevitable, pipeline bubble into the pipeline stages, in this case, is inevitable. We can avoid the hazard by using a pipeline interlocked or pipeline stall, as we can always do. The pipeline interlock will detect when the data forwarding will not be able to get the data to the next instruction in time. A stall is introduced until the instruction can get the appropriate data from the previous instruction. Great advantage of data forwarding is that it minimizes stalls and therefore there is no need for extra clock cycle. When there's data hazard and data forwarding cannot help, in that case, you need to put some bubble into the pipeline. If data forward can help, it adds some combinational delay, however, into the stages of the pipeline, which may increase the clock period a little bit. Additional data hazards can occur with memory accesses as well. For example, store and load instructions. It is likely that data memory read can be performed after a write in a single clock cycle. So if we look at carefully to the load use data hazard detection and prevention mechanism, we observe that the logic is similar. In that case, instruction fetch, instruction decode, register source 1 equals instruction decode, execute register source 2, or instruction fetch, instruction decode, register source 2 equals instruction decode, execute register source 2. Along with that, we need to have the control signal IDIX, mem read, being turned on. When the hazard is detected, we insert bubbles into the pipeline. But how? Well, a way to do that is to force control values in instruction decode execute register to 0 so that it will be resetted, and we prevent the update of program counter so that we fetch the same instruction for the next clock cycle again. In the meantime, we also keep the contents of instruction fetch instruction decode register intact for one clock cycle and then allow it to change in the next. So the first thing we do to reduce stalls is to try data forwarding, and if it ever works, great. No performance loss, no loss with regard to CPI. If not, then we would expect some performance loss. But one interesting question is whether or not reordering the instruction would benefit us when data forwarding cannot help. In that case, compiler would need to know the pipeline structure, and only then it can reorder instructions depending on type to minimize performance loss. This reordering is known as dynamic scheduling and is often a very, very challenging problem. All right, folks, so in this class we intended to cover basic pipelining concepts. We started our discussion with the basic pipeline idea and risks pipeline stages. Then we talked about performance when the processors support pipelining, This fundamentally helps us to compare different processes with pipeline stages. Finally, we talked about structural and data hazards and solutions generated for these hazards. In the next class, we'll hopefully continue our discussion on pipelining. Particularly, we'll touch base with control hazards and workarounds for the problem. So please feel free to drop any questions you might have about today's lecture into my mailbox, and I'll be happy to help you with your questions. See you later.